Welcome to Happy Path Programming. I'm Bruce Eckel.
I'm James Ward. All right, well, welcome everyone. Today we have with us Mark McGranaghan, who I used to work with at Heroku long ago. So good to have you, Mark. You can say hi.
Hey, thanks for having me.
Awesome.
And I'm wearing my Heroku shirt.
Yeah, you're wearing your Heroku shirt to celebrate the day of talking to Mark, but we're not going to talk about Heroku. That's been in my Twitter feed plenty over the last few weeks. Due to a security incident.
And I have some news, which is that the Summer Tech Forum is officially August 15th, the week of August 15th. So the 5 days there, and a little before and a little after.
Yeah.
And you can find out about it at summertechforum.com.
Or just search STFU.
I don't think that'll work.
That's not going to work.
I don't think that'll work.
No. Okay. Search for Summer Tech Forum Unconference.
And if there's not enough description there, the overview is we try and have experiences that are very much like this podcast. It's just conversations, and there are no speakers. There's no
except for lightning talks. We do some lightning talks.
That's true. We have speakers for 5 minutes at a time.
Yeah,
but those and the lightning talks can be on anything that interests you, not just technical stuff. And we've had, in fact, most of the non-technical stuff is probably the more memorable lightning talks.
Yep.
So, we have all kinds of stuff. It's all described on the website. As much as I can.
Hopefully people can join us in Crested Butte in August, and we'll do more of this.
Yes, exactly.
Okay, on to Mark. So thanks for joining us, Mark. And you have your own podcast, and I've listened to a number of episodes and really enjoyed it with Adam, also back from the Heroku days. And but now you're off doing a startup-ish called Muse. And so I want to hear about your journey to Muse and what Muse is and all that kind of stuff.
Yeah, so maybe to work backwards from the present, Muse is a tool for deep work on iPad and Mac. So we have this notion that there's a lot of good software tools for production work, like video editing or creating LaTeX documents or things like that. But what we were really interested in is the messy middle of thinking, brainstorming, ideating, sketching. And we wanted to create software that captured that process in the same way that a messy whiteboard or a messy desk might. So Muse is this multimedia canvas for facilitating that creative process.
And then, is it for mostly remote work?
Like collaborating with people not in the same room as you, or could you use it?
Well, right now, Muse is actually for individuals. So it's not yet collaborative. We can talk about that. That's an important asterisk, but it's for your own private creative process. For the same thing that you might use like a notebook for. People often use that for brainstorming and ideating and sketching. It's for capturing that thinking process.
Okay. So I'm going to ask the obvious annoying question, because I use Windows for a large portion of the reason that I use Windows is because it annoys people. But a lot of it is because the vast majority of machines out there are Windows. So is this always just going to be for iOS stuff, or what's your
for now, it's focused on the Apple ecosystem. And let me give you a little background on why that is. First of all, we did a lot of customer research in the research lab, which we can talk about. But we found that a very large proportion of creative professionals, as you might broadly define it, did use the Apple ecosystem, especially Macs and iPads. And that brings us to the iPad. And Muse actually started as an app only for the iPad, because we felt like people were really missing the capability and potential of that platform. We heard this story constantly. We called it the night dresser problem. People bought iPads with the aspiration of doing all this creative work, the sort of thing that you see in the Apple ads, like, taking advantage of the pencil and sketching, and it's like this very tactile surface. And then what they found themselves doing. Yeah, right? It's very common. But then, and let me know if this reflects your experience, what people found themselves doing was watching Netflix and then putting it in their nightstand drawer, because they didn't. And the reason for that was that there wasn't really software that really enabled that tactile, creative, expressive experience. But we thought there was potential specifically on the iPad. And there are other tablets available, but especially at the time when we started this a few years ago, iPad was by far the best, in our opinion, really the only one that was suitable at 120 hertz refresh rate, incredible display, very fast processor, things like that, that just made it most suitable. So who knows in the future?
Interesting that it's interesting that the iPad was kind of pitched as being this like creator device, like that it would be this like way that you could just express all your creativity.
Replacement for paper.
Thing. Yeah. But yeah, you're totally right. There was this huge software gap where it wasn't really.
And there are some tools on it. I mean, like things where you're manipulating images and stuff. Those are really nice on the iPad. Yeah.
Yeah, there were a few, like Procreate is, I think, a great example. It's maybe the biggest success story of an app that was specifically designed for the iPad, but that's a very rare exception. Most software that we saw, and indeed that we still see today, is what I call transliterated. They either took a phone app and made it bigger or took a desktop app and made it smaller. And you're really missing the unique capabilities and limitations of the tablet form factor if you do that.
Huh. That's cool. Well, I'll have to try Muse. I've
sure.
never tried it. Have you ever?
No.
Ever tried it?
No.
Yeah, I'll have to give it a try.
Yes. And so what kind of things do you capture? Does it do? What's its magic?
Yeah, so Muse, it starts as a blank canvas, and the first thing you can do is ink and erase, as you might expect. But then you can also bring in text, links, images, video, and you can combine them all on a canvas and move them around free form and group them and things like that. And then you can also nest these boards within each other. So you create this sort of memory palace of your creative thoughts where you have different boards for your different projects and ideas.
That reminds me of there's a tool in that's out of the Czech Republic that people would use for presentations.
Oh yeah, the one that like you could zoom in
around
and then zoom out, and it would like spin around.
And I can't remember
what it's called. What's the name of that one?
I don't.
Is that Prezi?
It was
Prezi. Yes,
that's
Prezi.
Right.
Yeah,
Elm was like they were building that in Elm or something along those lines, right?
That's
like
right.
The Elm language kind of came out of that.
Yeah, and
Prezi.
it sounds a little. I mean, that was purely for presentations, and it sounds like you're trying to solve a different problem, although it also sounds like this could be used for a presentation.
Yeah, and people do that sometimes, especially with the tablet. And we have this feature called a presenter pen, which is this disappearing ink that goes away after a few seconds. You can use it to sort of mark where you are and what you're talking about and stuff.
That's cool.
Interesting.
That'd be fun.
Okay. Yeah.
So tell us first about the journey to get to the company of Muse and kind of your startup journey.
Yeah, well, let's go back to the research lab that we spun out of. So the original founders of the lab were actually the original founders of Heroku, and that group, and then several of the people who would later join. They all came from this world of like enterprise SaaS, basically the typical cloud software that we all know and love. And there's a lot that's great in that world, but the founders of the lab, they had this hunch that there was something that we were missing and not exploring. And that was the original promise of computers as a way to aid creative thinking, right? Like computers have become very good at, well, social stuff like media and consumption, incredible advances there, and also enterprise stuff. Like we talked about Salesforce earlier, that there's all kinds of apps, but computers as a kind of creative tool, bicycle for the mind, we kind of lost the plot on that, we think, a little bit. And we had the founders had some hypotheses as to why that was. And
so the lab had a goal. It sounds like they said, we want to set up a lab to discover this original purpose.
Yes, the idea with the lab was to advance this field of, call it creative computing. And the reason that they set it up as an industrial research lab was the following. There's two well-known paths for advancing computing. One is the startup. And the startup is a very well-trodden path. But the thing about a startup is you need to be within, call it 1, 2, maybe 3 years of a commercially viable product for that to work. It's really hard to get venture funding for something that's, say, 10 years away. On the flip side, there's academia. And academia is amazing for generating all these great new fundamental ideas that indeed may or may not have any application to the industrial world. And that's kind of the beauty of it. And often those ideas do find their way into production, but it might take, say, 10 or 15 years. And so there's this missing middle, this valley of death, where if you're 5 years away, say, from an idea, you kind of see it out there in the distance, but it's not quite commercializable yet. you were kind of out of luck. And the way that we used to solve this back in the day was the Industrial Research Lab. And that's this organization that brings together insights from academia and industry and targets that, call it 5-year time horizon. And that's what the lab founders felt like was the right thing to go after for this creative computing space, because there were all these pieces that we saw around, and there was this potential and this need that they saw, but it needed a little bit more time. So that was the idea with the lab.
So this is like the Xerox PARC thing, which it's wild how many of our current things in computing trace back to Xerox PARC and the research that was done there. So trying to like do that same thing, but specifically focused on creativity, the creative computing connection. Right. That's cool. So, so the some of the Heroku folks, all the Heroku folks, created this research lab and
yeah, the Heroku co-founders started it, and then several other folks ended up joining as principals. Peter Van Hartenberg relatively early, and then myself later.
Awesome.
And then
it's like getting a band back together.
Yeah, a little bit of that. But also it was one of the reasons the lab was and is so amazing is that it has this particular talent model where it brings people from all over the world, literally, but also in terms of different stages of their career and for different time periods and in different capacities. And so it ended up being this really cool, fertile ground for ideas around creative computing.
So when it was started, there maybe wasn't ideas around what was going to come out of it. It was just like, all right, let's start. Let's get these people together and start brainstorming. And
yeah, I think I would have to go back and look at the original pitch deck to see what exactly they knew at the time versus they know now. But I think there was these hunches of, we feel like we could be doing better for creative computing. I think there was a hunch around touch interfaces and tablets, where if you go back 5 years, tablets were really breaking out, and you could see if you mapped it forward 3, 5, 10 years, how they could become this incredible computing platform. There was some hunches around the technology, what eventually became local first. But it needed a little bit more time to fully play out. And they wanted to give it that time so that you weren't reaching only for things that were within, say, a year. And you wanted to have more of an exploratory attitude, as you might in academia, but sort of grounded in these inputs and factors that you're drawing from the industrial world.
So did does the lab still exist, or did they dissolve it once you started this?
The lab still exists. It's going as strong as ever. There's actually a lot of great publishing coming out of the lab. You can check out Ink and Switch on the search engine.
Nice.
And
Switch, that's fun.
It tends to work as a series of projects, often in different lines of research. So the lab would have, typically a PI at the lab would have some hunch of, I read this paper on CRDTs, for example. It seems like there's something cool there. Let's put together a 3-month project around it, maybe 2, 3, 4 people, and try to build a prototype app that uses CRDTs. Or we think that something's wrong with authentication. Let's explore that for a few months and do some prototypes around using, I don't know, barcodes for authentication or something. I don't know.
Yeah.
And then, but then over time, you tended to get these patterns, and you got these strings that you were pulling on that seemed more and more viable. And 2 of those that ended up being relevant for Muse. So one is what became local first, and we can talk a lot about local first.
Yeah.
But that was a very important one, this new way of architecting applications. And the other was touch interfaces and tablets, and how to design those to be suitable for especially this type of creative work. And what happened was those 2 lines of research got fairly far advanced. We had done a series of projects in both of them. We felt like we were really onto something, but that to further explore and realize them, you would need to bring them into the commercial world. You need to test them with more real users, and you need the corresponding capital to affect a real product. And so at that point, we spun out Muse. So Adam, Yulia, and myself, who were 3 people working in the lab, spun out as co-founders to start this new venture. And the lab's still going. But this is now a commercial entity.
Nice. And how long ago did Muse spin out?
I want to say about a few years ago now.
Yeah. Okay. And I saw that you just had Muse 2.0 released this week. Is that right?
We did. And the keystone of this was this local first idea, which in turn enabled us to bring Muse to the Mac and to synchronize across devices. And until recently, Muse was like a single player single device app, like kind of a classic App Store app that you just installed and ran locally, and all the data was local. And that actually works quite well. It works the same way that like a notebook works. It's always right there. It's always fast. It's not going to go away if the internet's down or something. But we wanted to start to bring in some of the capabilities that you expect from like a normal cloud app, and so that's where Local first came in and allowed us to have both a Mac app and an iPad app now.
Okay. So initially there wasn't necessarily like a cloud sync model for the data, or is that right? Like
right. Yeah. The Muse 1 was all local, and we've from the very beginning we've expected Muse to be multi-device. It should be on at least the iPhone, the iPad, the Mac, and the web, and to be probably to be collaborative. But we had to start somewhere, and we chose the iPad because the iPad is the device most suited to this creative brainstorming idea. Like you want to sit back in a comfy chair and just do some thinking, do some reading, do some annotating. It's not the phone and the desktop are not as suitable, but those are important complements to the process. For example, the phone is where you're reading Twitter and you see an interesting idea and you want to capture that for later thinking and noodling. And the desktop is where you do like your power workflows. You're organizing the 100 PDFs into different folders, or you're doing an outline that summarizes everything that you've learned to date. So you need each of these devices for different things, and therefore you need your entire corpus of data to be synchronized across them.
Yeah. Cool. So, okay, let's get into the Local first sync, because when I heard you all talking about it on your podcast, I was like, oh, this is going to be fun, because we've talked about CRDTs a little bit and distributed systems on the podcast. So tell us about Local first sync and the whole thing.
Yeah, I think it makes the most sense to talk about it in terms of how we got here. So there were two worlds previously. There's a desktop world and a cloud world. And the desktop world, you have to go back a while now, but this is when like you had Microsoft Word, you would open up the app and you would save a file to disk with your edits. And there are actually a lot of nice properties with that. For example, you can read and write when you're not offline. It's always very fast, at least as fast as your local disk. Especially with standard file formats, you have a lot of control. You can CP or rsync the data around to get backups. Like there's a lot of things that's nice about that. And then you can even extend that a little with something like Dropbox, where you take that model and you add a little bit of multi-user collaboration on top. That's world one. The other world is the cloud world. And the example I would give here is Google Docs. And Google Docs is the amazing gold standard for real-time collaboration. You can have 20 people in a document, everyone's typing in different places and every character keystroke comes in real time. And that's great. But then that has all these downsides of, if you want to back up your own data, you're kind of out of luck. And certainly if you're offline, you're out of luck. And we had this hunch or this desire to get the best of both worlds. We want the character by character real-time collaboration, or at least the ability to do that. We want that your data is just available whenever you're online, it's available on all your devices and with all your collaborators. But we also wanted the performance, the reliability, and the user agency of having a full copy of your data on each device. And it's very easy to list Desiderata out and say, I want all these things. The problem was that if you use either of the standard technologies, like call it regular files and folders, and even with Dropbox type stuff on top of that, or the first generation of cloud sync technologies, you couldn't do it. You had to go back to the beginning and redo the architecture from first principles so that you were able to get all of these qualities in one thing. And that's where this research on CRDTs comes in. So Martin Kleppmann.
Can we spell out CRDT?
Oh yeah, good call.
Yeah, so CRDTs are conflict-free replicated data types.
Shouldn't that be CF? RDT?
Yeah, they don't choose the right letters because CRDT sounds good.
Yeah, it does sound good. It works well.
Yeah.
Okay.
Yeah, so give us some of the background on CRDTs so first of all, I'll say that when most of the time I hear about CRDTs, it's kind of like people are like, we discovered this thing and then later realized it was CRDTs. Did it happen that way for you, or?
Well, so for us, it's actually a really good example of the industrial research lab at work. So we had gotten in touch with Martin Kleppmann, who's one of the world's leading academic researchers on CRDTs, and he was doing this incredible work on practical CRDTs. And I can't take any credit for this. This is people who were earlier in the lab than me, but they basically saw this and made the connection. and plotted out several years and said, we had this problem. We want what would eventually be known as local first software. We want all those properties. We're missing the technology. CRDTs could be it. Now, at the time, and even to some extent today, that was a very long ways from reality. It's a very academic concept. You read these papers, there's like these incredible proofs with all these weird symbols. Like it's not practical for most application developers to deploy this in a production app. Yeah. But that's the beauty of the research lab. You can bridge that gap and try to connect the dots between the academic world and the industrial world, which we started to do through a series of prototypes and eventually with the spin out.
That's cool. Yeah, and the thing that I love about CRDTs is that they are based on math. And I forget who said this quote, but there was a quote from, I think, a Strange Loop presentation, which was something along the lines of, if you can use math to solve a problem, you should. And I love that like CRDTs are based on math. And I think what's been interesting over the last few years is people like figuring out how to build something on top of the math, but not make the like end user experience be the like math experience, be like the business,
functional programming. I think has this problem.
Yeah, exactly.
It pushes math.
It pushes the math onto the programmer.
No, you got to understand the math though. Yeah. Because you won't know what a monad is if you don't understand the math.
That's right.
Yeah, I think functional programming is actually a really good example because it can and often is, in the same way with CRDTs, presented in this very mathy way, like these incredible formulas and proofs and complexities. And you can even get, as a developer, access to libraries that fully expose that to you. Go wild.
Yeah.
But at the same time,
but you're trying to solve a business problem. You're like, you've got a business need.
Just go. Yes, we believe the math.
There's in both cases, there's what is a very simple core. So in functional programming, it's just like if your functions don't have side effects, you get all kinds of nice benefits, and you don't need to use Haskell or whatever to get those things, right? It could just be in your regular Ruby program.
Any programming language, yeah.
And same thing with CRDTs. There's incredibly complex CRDT research and even libraries that you can use, but you could also just take this core, which is if your data type has certain properties, you get benefits that are extremely useful in a local first world.
Yeah.
Okay. Also sounds like monads. It's like, we got a data type and we got these other characteristics. So can you give us the big picture overview of how CRDTs work? Is that possible with the math free?
So it's interesting because everyone says like CRDTs are kind of a buzzword now, but the way that we use CRDTs is actually extremely simple. We use these incredibly simple, almost trivial CRDTs. Again, it's the core principle. So just to very briefly describe how our system works.
Yeah.
We have objects, sort of like you would have rows in a table, same sort of concept. And then objects have attributes. And the whole problem here is you need to decide if multiple devices write to a given object and attribute register, who wins. And so you can take perhaps the simplest CRDT possible, which is last write wins CRDT, and use that to manage the merge. So basically each edit has a timestamp, and we can talk about the timestamps. They're more complicated potentially than a simple time.now. But there's no magic here with the CRDTs per se. It's like 3 lines of code in the client which says if timestamp greater than other timestamp, take this value. It's more in our case, it's more the principle of having this simple but principled way of thinking about how you manage data coming from multiple clients. I think the more like interesting and complete picture is the whole local first thing. And so this is just like a kind of key enabling insight. And there are use cases where you need more sophisticated CRDTs. The most common one is text editing. Like if you're doing real-time text editing and you have multiple people in the same block of text, then you do need more complicated CRDTs to manage it. But the entirety of our application and most applications, you just don't need stuff that's that complicated with respect to the CRDTs themselves. It's more like everything that goes around it that's the real secret sauce.
Well, and it sounds like it's such a fundamental architectural decision. You have to make this decision from day one and do everything around it.
This is an extremely important insight from looking at trying to migrate other systems to getting all the benefits of local first. So we can take two examples. Dropbox, because you have this fundamental abstraction of like the whole file as a sequence of bytes. If you want to manage edits at any granularity smaller than that, you're kind of hosed. Like there's just no way to do it. And that's why you get, if two people edit the same Word document in Dropbox, there's going to be a conflict. I don't even know what Dropbox does these days, but it's going to be a mess.
Yeah,
there's no way
to resolve that
to
conflict,
deal with it
because you don't have enough granular information to resolve that conflict. Your granularity is the document, not the text block or something smaller.
The event,
correct?
The event,
and likewise with the cloud, with the typical cloud world, if the only canonical store of a client's data is on some centralized server, there's no coherent way to get all the benefits of local first on individual clients. You see people trying to get at around the edges. So it's like offline mode and caching, and it basically never really fully works. It certainly doesn't give you all the benefits that you would hope from a system like Git, where everything is fully and properly local. So you have to do it from the very beginning.
And yes, from the very beginning, here's why CRDTs are important, is because in like the Google Docs model, you have a centralized decision maker that is deciding what to do in the presence of conflicts.
Right.
And that's on the cloud. The cloud is that decision maker. And in your case, you wanted it to be a true distributed system where there isn't a centralized decision maker. And that's the whole value of CRDTs here, right? Is that you don't have to centralize the decision maker to resolve the conflicts.
Can you just use blockchain?
Oh God!
Oh no!
Absolutely.
That is
just every key press will cost you $10 and take 10 minutes.
Yeah, exactly.
Well, that will make me very careful when I'm writing.
That's a good point.
So that's a plus. That's a benefit.
Right.
Okay.
Benefit. Yeah.
Yeah,
so
that is in fact the key
CRDT.
property of CRDTs. It's that if you have a set of edits or changes, once any clients that apply all of those changes, regardless of the order or how they're batched or when they come in or whatever, they're going to end up with the same result. And you don't need a central
the same state without a centralized coordinator.
Yeah, the same data object or whatever, without a centralized
making me
coordinator.
Think of our Kafka interview.
Yeah, we did. Well, we talked about CQRS and event sourcing, which aren't CRDTs per se, but have some similarities.
But just the idea of looking at everything in terms of events and then figuring out. Well, in Kafka's case, they just capture them, and then it's up to you to figure out what to do with them. But here you're talking about how to decide. Okay, here's what we can resolve that. But I can understand why you need mathematicians to figure this out, because there could be holes.
Yeah, why having lawful algebraic stuff underneath the covers is important for
especially for
being able to get to the same resolved state.
Yeah, you have to think about it in a very principled way. And with respect to CRDTs, especially for the complex ones, like I mentioned, you need to be very rigorous, because it's super easy to convince yourself incorrectly that the CRDT is correct, but then you get into these edge cases, especially with text editing, where things go wonky.
It's always been an issue with concurrency too. It's really easy to go, my concurrent program is fine. It doesn't have race conditions. It doesn't have contention.
Yeah. A side note on that, I just learned that Google has a tool called Thread Sanitizer, I think, that will like take concurrent code and I think it runs it through all sorts of different scenarios that you usually aren't thinking about as a developer, and then it tells you like, oh, you have a race condition given this particular scenario, and so it's kind of a fascinating tool.
That's impressive.
Yeah,
if it works.
Yeah, we need like a TSAN for CRDT or for replicated state, distributed state. But or you could just use CRDTs and trust that the math is correct. So walk us through the architecture of I'm on my iPad in the Muse app and I do something. What actually happens?
Yeah. So when you're on a device locally, whenever you make a change, that emits called an edit, and that edit goes into your bag of edits. And to a first approximation, you're just saying all the edits that you ever made in your bag of edits. And based on the bag of edits, you can do the CRDT merge to get up to the current state of your application, and then sort of react like you're going to take that current state, feed it back into the rendering engine, and it will produce the corresponding update on the UI. Now, if you're offline, that's it. And if and when you are online, that edit has, call it like a write bit or something that indicates whether it's been pushed up. And so when you're online, that edit will get pushed up to our sync server, and that will get persisted in your kind of cloud stored bag of edits. And then B, as other clients come online, they will receive that edit. We can talk more about the mechanism if you're interested. But basically, that edit will get conveyed out to all the other devices corresponding to your user account. And then they'll go through the exact same flow of, there's this new edit, put it in the bag of edits, merge up to a new state, put that into the UI to render, and then you get the update.
So the logic doesn't care. I think this is a critical piece where the logic doesn't care if the edit event came from your own on-device, I made this here, or came from another device through the server.
So you push it first, and then on your local machine, you do the edit. Is that correct? You push it up to the cloud first?
It's more like you write it, and you affect it on your own system first, and then you can almost think of it as like a background process. And in fact, there is some batching that happens here.
Okay.
That's doing the network communication management, and that will say, okay, in the last 50 milliseconds, there's these few other writes. Go ahead and send a batch up to the server with these writes, and those will get conveyed out. And so this is one of the incredible benefits of local first. That whole first loop of you did a write and it gets rendered, that's as fast as your SSD, right? So that can be essentially instant. It's not doing a round trip to Virginia or whatever to get to AWS and then come all the way back with a new rendered web page. And this was one of the huge motivations for local first. It's not physically possible to have software be fast enough if it has to jump over that long of a network hop. It has to happen locally. So you do everything to update your state locally, and then in the background, on the order of maybe it's 10 or 50 milliseconds, you can get this state out to the other clients. But also go ahead.
How do you make sure it gets to the other clients?
Yeah, well, that's where there's some accounting basically on the client where it says, okay, when you write a transaction, it's going to say who wrote the transaction, you in this case, and it will say what's the state with respect to the network. I've never tried to send it. I'm currently sending it. I've confirmed it's sent. So when you go to write to the sync server, that's going to be a request response where you're going to say, write this pack of edits, and once the server has successfully persisted them in the database, it will write back to the client and say, okay, I've confirmed that I've got these. You can count these as safely synced. And then the client can, at that point, go into its accounting and say, okay, this pack is synced. So I know I don't need to resend it. And if something happens in there, that's all idempotent. So the client can resend it and it's fine. And the server can resend it back down to the other clients. That's all fine. So you just need to happen at least once. This, by the way, is another benefit of CRDTs and generally of thinking in this way of when everything is idempotent, everything becomes a lot easier.
This is what Victor Kling calls effectively once delivery, because a lot of times people say they want exactly once delivery, but it's I think provably impossible to do exactly once delivery. And so to get to effectively once delivery, you do at least once delivery. So your system can pretty easily guarantee that it's going to be sent at least once to the destination. But then if the operation on that event is idempotent, then you get effectively once, because it doesn't matter how many times your event is sent. If it's idempotent, you could do the same thing multiple times and not have to worry about it, doing something wrong.
So maybe this is a minor detail, but the way I'm seeing this happen is I cause an event, my local iPad responds to that, and at the same time it's put it on a queue to be sent to AWS, and then my local machine is eventually going to see that event come back like everybody else in that network, right?
All the other clients.
And it's going to ignore it because it says, "Oh yeah, that was mine. I sent that."
So there we can, because we send up when we write these packs, we write the device that's sending it. The server, when it's conveying out these updates, knows that it doesn't need to replay those. It would be fine, but there's no need to do that because we have the data to be able to do that accounting. So it will just send you all the rights from devices other than yourself.
I see. Okay. Yeah. But then to make sure it's gotten onto the server, you just have some kind of handshake. So it's like, yeah, I got
Yeah,
it.
it's a confirmed
Okay.
request response. And then on the other side, when devices are pushed down updates in near real time, the server doesn't consider those successfully written, conveyed to those clients until those clients respond to the server, which they're only going to do after they've synced the write to their own local database.
Okay, and then you mentioned that time was tricky, which I would think it would be, because how do you decide? Well, I don't know. I mean, where does the time come from?
Yeah, who decides time?
Yeah, who decides what the time is so that you can say, oh yeah, this event happened before that event?
So this, in general, in distributed systems, this is a really big problem. But for our case, it's actually not proven to be a big issue, and neither by the way of conflicts. Whenever we talk about CRDTs or these like distributed synchronization systems, everyone always brings up conflicts and timestamps and vector clocks. And our experience over many years of working in this lab is that basically it's not an issue, at least for the use cases that we're looking at. So abstractly, our timestamp is 64 bytes of data, and you can put whatever you want in there. Currently, we actually just use a regular vanilla Unix timestamp. We will probably, when we have multiple users, where you have more issues potentially with clock skew and users stepping on each other, we'll move towards what's it called? We can put the link in the show notes, but there's this specific type of timestamp that James Long at Actual Budget first used to our knowledge in this setting. But it's basically a timestamp that still fits in 64 bytes, but has some of the properties of a vector clock. So you can get logical ordering within certain constraints of updates, but it doesn't have the problem of most of the, call it more academic CRDTs, which have vector clocks that blow up in space. This was the thing. We were not willing to compromise on performance with the system. It had to be as fast as like a purely local SSD based app would be. And so if you have anything that blows up in the number of clients or edits or history, anything like that, it's already over. So and it's a good example of the sort of the industrial compromise that you have to make with systems like this.
Well, yeah, and it seems like you could just say that the clock is a way to resolve these things, whether or not my timestamp is exactly the same as yours. Most of the time, sometimes maybe mine's lagging behind yours. Okay, so yours will get in ahead of mine. But how often is that going to be when you're doing this kind of interactive thing, things that are that close, does it matter, or is it just like, we'll just use this to resolve these things?
Yeah, with our current setup of this being only for one user, you just tend not to have that sort of unexpected like clock skew and corresponding out of order versus what you would expect. I think it'll become a bigger issue with multiple users and collaboration. And then relatedly with conflicts, like we worked on these systems for years now between the lab and Muse. And I don't think we've like ever had a real issue with conflicts. Maybe there's an asterisk around like collaborative text editing that becomes a bigger problem. But in practice, humans know not to step on each other. So if you're both at a whiteboard, you're not going to like have a conflict of you both try to write to the same space because you see what each other are doing. You're not going to like mess each other up. And generally, people know what they try to know what other people are working on, trying not to step on each other. So for that reason,
I do
and
have
because
two hands, and I could like use Muse on my iPad and my iPhone at the same exact time, and like make a change, and then I'd be stomping. But I wouldn't really do that in real life.
Yeah.
Well, and you couldn't do it at exactly the same moment.
You maybe could. Well, it depends on what exact means. But I could have my fingers on, touching both devices at the same time. But why would I do that? Is I think Mark's point is like
you would, and it would just like go, oh well, this one I've decided this one is first, faster, and so I'm going to do this, and you go, oh okay, it's not.
And most often I'm like picking up my iPad, doing something, picking up my phone, doing something. Mm-hmm. Like there is a time shift between those two interactions.
Yeah, it's just an empirical matter. It's not that high up on the list. It's probably not in the top 100 things we've run into trying to build a system. No. But also, all the data is there. So if anyone ever had an issue with what they believe to be incorrect conflict resolution, we can just go in the database and promote one of the transactions over the others. But literally, no one has ever asked us about that. So it's just
right, right. Okay,
yeah. So you're doing then
What?
some kind of event sourcing type of thing where you're keeping all the edits, and then tell us more about that architecture, that studied architecture.
Yeah. So the logical architecture is that currently it's that each user has a log, and the log is sequence and has sequence numbers, and each device then has a read head on that log. It's kind of like Kafka, where each device has a read head
Yeah,
on a log, and it advances when they've confirmed that they've successfully processed those updates to their satisfaction. And then it becomes quite a bit more complicated with collaboration, because then you need something like, because we want to support granular collaboration where any individual document or board or group of documents could be collaborated on with any arbitrary set of people. So then you
yeah,
would need something more like there's a logical log per document, and you have a bunch of read heads corresponding to all your different documents. That becomes more complicated. But the basic idea is that you have these logs and you use that abstraction to get the data out to clients. And for the actual storage, we use Postgres for the transactional storage. And we could also talk about like the real time aspect and the large binary blobs. That was one of the important
yeah,
considerations that we found. But that's the basic model.
yeah. I'd love to hear more about that. Okay, so typical like sequential log of events, and then if I go open a document in Muse, does it always every time like replay all the events for that document from the start, or is there some like snapshotting or something?
Yeah, there's basically caching. The exact way that we implement this is not my wheelhouse is more on the server side, but I think I can give you a high level, which is that there's basically a table or a view that corresponds to the current state of all of those object attribute registers that I mentioned. So it's sort of like a regular SQL table where you can like select star where attribute name is this and value is that, and it doesn't need to query the entire history of the universe to do that. It just looks at the current values.
Yeah, so that's like
In
the
that respect,
CQRS. Like it's like client-side CQRS, where you're like materializing a view based on the logs, and then based on your sequence number, like how far along you are in the log with your materialized view.
right. And that's also up to the clients. Like we've also the main client that we've implemented is the Swift one for use in our iOS apps. But we also have a little JavaScript client, which is more for testing and experimentation. And early versions of that did just slurp up the whole history into memory and build up a big hash table. So it's kind of up to the client to do whatever they think is best,
Yeah,
and you have the flexibility to
but
choose
the
that, and
log
also
is
to
the
like
truth.
re-choose it. Yeah, over
Yeah,
time.
the log is the truth, and so you can decide how you want to deal with the truth.
Yeah.
Yeah,
One of the
yeah. So
other go
go
ahead.
ahead. I was
Well,
going to have you go into like serialization and efficiency of events and
yeah,
all that kind of stuff. But
I do have a lot to say there that, 'cause like I said, performance is so important to us. I want to make
yeah,
one point about the architecture. And to make this point, I want to go back to the original experience that convinced me to join the research lab and to work on local first. So I was
yeah,
meeting Peter Van Hartenberg, who now runs the lab, in a coffee shop in San Francisco. And he was showing me this new prototype of this little demo called Pixel Pusher. And Pixel Pusher was a pixel art editor where you have these, highly pixelated
uh,
images that you can edit, choose the color and so on. But it was real time local first collaborative. And so the demo he showed me was he had two instances of this Pixel Pusher app, and they were synchronizing and collaborating in real time. But there was no server. The entire app was just the React app that he had built,
yeah,
and they were talking to each other. I had spent my whole career building these servers that are incredibly complicated. It's a huge pain to manage all of them, and then you have to have your data model on the server and on the client, and you got to keep those in sync. And it was incredible to see there's just one code base to implement this app that is real-time collaborative, which up until that point we had associated with complex cloud infrastructure.
yeah.
Now, we
Having the
explore
centralized coordinator, which has scalability issues traditionally.
yeah, and so here's some subtlety around that. We explored in the lab a lot the idea of doing totally peer-to-peer collaboration and
Yeah,
synchronization. But there are two
yeah,
big issues with that. One is doing peer-to-peer connections on the public internet is, let's just call it, troublesome. There's all kinds of obstacles in your way. For example, if you're at a cafe, often the router will block peer-to-peer connections for, frankly, pretty good reasons.
yeah,
But there are all kinds of other issues with NatHole punching and so on. But the other issue, maybe even more fundamental, is that people have this reasonable expectation that if they, say bring
lose
up
their
their
device.
they lose their, like, okay, yes, say they lose their device. They want to be able to get all their data back. Or the simpler case is we're collaborating on a document. You make some edits in the document, and then you go to sleep, and then I open up the document. I don't want to have to wait till you get up to send me the edits, right? I should just be able to get them. That's for better or worse, that's the expectation that users have. So we ended up with this model where you still get a lot of the benefits that I just described, but you also get the benefits of the cloud. And that's to have this very simple content agnostic synchronization server. So the synchronization server basically just stores these logs of opaque blobs and shuffles them out to the devices as needed. Our sync server is a few hundred lines of Go code. It knows nothing about boards or cards or Muse or ink or any of that stuff. It doesn't need to, right? It's just shuffling these bits around. And all the logic about the data model is on the clients. So it's much easier to scale and maintain and eventually to do encryption and so on. We can talk about that on a server like this that's very simple. And by the way, it's totally generic. Like I said, there's nothing having to do with Muse in the server. So in the same way that it's easy for us
on the server that's here's a board, here's a whatever. All it knows is I got an event and here's what I do with that event.
So what's interesting, I'm just thinking more philosophically about this, is that is actually serving you rather than trying to control you. I guess I'm thinking of this in terms of hierarchies in general. It's sometimes you do need a central thing, but it needs to be serving you and not controlling you.
Yeah.
Yes. And in fact, one of the 7 desiderata that we enumerated in our local first position paper was user control. That's number 7. And, we want users to have the sense of they control data in the sense of they can, they obviously control the schema, but they can get a full copy. They can take it somewhere else. You can convey it by a USB stick on carrier pigeon, whatever. It's your data. That's a really important benefit.
Yeah. So in that case, the server is there for the user. They're serving the user, not the coordinator that's making the decisions around which write wins.
and how do we translate that into an organizational structure? That's my next question.
Yeah. CRDTs for organizational structures. Yeah.
Yeah. So anyway, maybe we can. You had asked about the
serialization.
The serialization protocol. Let me add a little bit more color on the architecture, because we had talked about this idea of ephemeral and transactional blob data. This is, I think, is really important. This is a good example of where there's a bit of a mismatch between academia and the industrial world. So when you're building a real-time collaborative app, like you're building a real-time collaborative video editor, there are 3 types of data that are very important. The first is transactional data, and that's what you usually see being conveyed and managed around with CRDTs. This is stuff that you would write in a SQL database usually. And CRDTs, as we know them, are good for that.
You get high ACID compliance with those.
They need to be durable.
You're
pretty. They need to be very durable, very reliable. The amount of data is extremely small in the scheme of things, and so on. Then you have what I would call ephemeral data. So an example of this is you have your finger on a card and Muse on a tablet, and you're moving it around, and you on the other side are seeing that card move around. You want to see that happen as fast as is physically possible given the network distance between us. But you don't need to save the whole history of 60 frames a second of where this card was for all time, right? It's ephemeral, it's best effort, it can be dropped. And then binary data, that's just these huge blobs. You have big video files or big images. And that's also a totally different shape. It can't be conveyed in the same channels. And so one of the insights from our research is that you need all 3 of these, and they have to be very coherent with each other. So for example, the ephemeral data, when you're moving a card around, whether it's ephemeral or transactional, should just appear to the developer as a flag. This is ephemeral, I'm moving. Okay, my finger's off the card, it's being let go, flip it to transactional. Whereas under the hood, it's going to take a completely different code path. It's going through different services and everything, right? It's completely different, but it needs to be presented to the user as being a coherent API. And likewise with blobs, that's going to go on a totally different storage path through S3, but the way that transactional data relates to blobs needs to be very consistent. Anyways, that's just an important.
That's a really good insight, because I think that part of what you have discovered, and I think other people are beginning to discover, is that we've tried to shove all data and all rights into the transactional model, or maybe into, I don't know, a NoSQL model or whatever. We try to say everything can fit this one model for data storage and data durability and data. We try to one size fits all data in a lot of different ways. And it's interesting that you were able to like categorize three different buckets of needs that you have around data, and it totally makes sense
And
when you explain it. Like like not everything is the same shape, and not everything needs the same durability, and not everything needs the same guarantees and all that. So makes
Hmm.
total sense.
yeah, and that brings us perhaps to the kind of networking and protocol side.
Yeah.
So I mentioned before how the sync server is just shuffling bytes around. So that implies this interesting separation into two protocol layers. There's what we call the network layer, which is how do you shuffle the bytes around? And there's a totally separate layer called the app layer, which is the schema of Muse boards and cards and ink and things like that. And in order for the server to not have to know about the inner layer, you need two layers, right? It might sound obvious, but it feels a little weird when you're developing the system and you have like these schemas stacked on top of each other. So then to go from inside out, when you make an edit, you will encode a transaction, and we use protocol buffers for encoding. We can talk about how we arrived at that, but it might not be too surprising to your listeners. You encode this as protocol buffers, and then you basically batch all those up, and you can optionally compress them and so on into a network level message, which is going up to the server and saying, for example, sync these packs durably, or perhaps sync these or convey these packs ephemerally, and so on. And again, because
So you
performance
tell
was
the
so
server when you send the message, you tell it which of those three buckets of data type of data you're in when it
yes,
sends the message.
that the server needs to know because it's going to send the data on completely different paths. So, for example, the data inside the app data looks basically the same. It's saying the card XY is this, but if it's going through the ephemeral path, the server is just going to immediately bounce it on a best effort basis to the other clients that are
Yep.
connected for that document.
Like a super quick broadcast loop, just like
right,
ephemeral
and
data.
furthermore,
All right, like
it's
skip the
best effort.
database
So
call.
yeah, and it's best effort. So if the server is saturated or the client is behind, I'll just drop it and say, too bad you missed this, 1/60th of a second of an update. Whereas the transactional one, that's a completely different path. That first needs to get written into Postgres, and then it needs to be acked back from the client and so on, and then it gets pushed out to other devices. And then obviously the binary data in S3 is completely different. But the stuff inside is the same. So when the client receives, whether it's an ephemeral or a transactional update, it will unwrap it and see, this card is now XY and plumb that through and get the update.
Huh.
Do you ever put data in more than one bucket? Or is it always one or the other?
Always transactional or ephemeral or
blob?
blob.
Well, a given write, mostly they always go in one bucket or another. The example of moving a card on an XY is interesting because you could, I'm actually not sure if we do this, but you could imagine a world where when you're moving a card, you send every single update, including the very last one where you're dropping it as ephemeral, because that update will arrive, call it 5 to 10 milliseconds sooner. And then so they can get that update as soon as possible. And then the transactional update will come and it will basically be idempotent because it will already have the XY, but it will also know at that point to persist it, which is going to take longer. So there's a little bit of overlap, but they tend to be in separate. And I could also imagine a world, we haven't done this yet, but you could also imagine a world where you do big compression in the batches, like take the last years of edits, put them into a single file, gzip the whole thing. At that point, that would be too big for putting in a Postgres database. So you might put that in S3, but you would know it would have appropriate metadata to indicate that is, when you unwrap that at the app level, that needs to be treated as app data.
Yeah, that makes sense. Does the batch from the client always contain a homogeneous set of data types? Like is it like you batch on transactional data, like only transactions, or and then you batch on only ephemeral?
Yeah. So first of all, batching is very important. This is one of the basic insights of high performance distributed system. Like basically there's batching at every single level. You have batches of batches of batches, which is a little bit annoying, but it's the way that you get the best performance. And the way it's currently architected is there's a message type for each type of path, whether it's like, transactional write or receiving transactional data. So all the messages within that are going to be of the same type. These are all durable writes that should be. And that's helpful because, like I said, these are going through completely different code paths. So it wouldn't be super helpful to separate these. But there's also batching at the connection level. So this is a single persistent connection. It's a WebSocket connection, actually.
Yeah.
And you can have arbitrarily many open requests with the server. So you could say, for example, one after the other, send these ephemeral updates, send these durable updates, even before you get any response from the server. And the server is going to say back, basically immediately, okay, ephemeral received. And then sometime later, you'll go back to the durable received. Or you could open up, 32 different writes to the server at a time and use that to saturate the network link, if you can, to get all your updates up. So that's another way where you do batching.
Yeah. So batches of batches.
Okay. Now, did we get to serialization?
Oh, you said protobuf. So yeah, tell us more about protobufs in your use.
So the story here is there's a few desiderata that we had around protocol buffers. There needs to be a schema. The schema needs to be, or around serialization rather. There needs to be a schema. The schema needs to be evolvable. There are a couple of critical data types that we needed to be in the schema, most notably like byte slices, which, for example, rolls out JSON. So it needs to be very fast. It needs to be binary format. It can't be text. That's not fast enough. And it needs to be in all of our key languages. So at least Ruby, Go, Swift, and JavaScript. And I scoured the whole universe. And I came to the disappointing conclusion, it seemed like the only option was protocol buffers. And I did this very sad tweet, which basically explained that. I've searched everywhere. Is there another option that's better? Or is it, unfortunately, as you already know, protocol buffers? And that seemed to be the case. And, protocol buffers are basically fine. It's conceptually almost exactly right. And the tooling is a little bit goofy at times, but it basically works fine. The one thing that I wish we could have gotten is, what's it called? Zero copy reads.
Yeah.
And some of the newer serialization systems do this where you don't need to kind of read and process the whole thing. You can just say, I want to read this attribute, and then it knows to go to this byte offset and just zip, read those bytes. So that would make it a little bit
lazy reads on the bytes instead of having to parse the whole thing.
So I think you described this in functional programming as lenses. Is that right?
Maybe could use lenses for it. Lenses are mostly a way to have a functional query of an object graph and then provide mutations on pieces of that object graph and get your copy out when you apply your lens to it. But
there's one other tricky piece with serialization and schemas, which is these two different layers. So there are simple cases like take the ping request, which is the simple request in our protocol. Request and response. There's a fixed set of attributes on that. Actually, I don't know if there's any attributes on that request, but maybe authenticate request. Okay, so the authenticate is always going to give you your credential to the server, and the server is going to reply back with either success or an error code. And so that's great for protocol buffers because it's fixed. It's basically going to be the same forever. But then there's a problem of what do you do about all the application data? And remember that this data is in this form of what we call atoms, which is object ID. We also have the scope ID, the attribute name, and the value. And if you think about how you would typically use protocol buffers, you'd have a schema that has things like boards and cards, and those things have these attributes. But we can't do that because our data model gets pivoted into these atoms. So instead, you have this sort of weird thing where you have a protocol buffer definition for atoms, and you say that has this ID and this attribute name and this value. But that pivoting is honestly a little bit weird. I don't think we have the perfect answer for it yet. No. But it does become it's kind of one of
the agnostic to the domain,
right? So you actually end up having basically two schemas. You have the way that you encode everything, which is in protocol buffers, and then you have the application level schema, which says you should basically expect to see atoms for a type board that has title and width and height, and
so you create this mapping from atoms to the actual domain.
Yeah, to domain objects, and it's kind of weird because you need two different schemas and they can't be the same thing because they're just totally different. They can't be protocol buffers, for example, and so that's been a little bit challenging. But it basically works.
In your Postgres database on the server, do you store the actual proto message, or do you deserialize it into the atom data and then store the atom?
We store the binary data. So typically, when you push up to the server, call it transactional data, it's basically going to be a bunch of serialized atoms appended to each other with some metadata around it. But the server doesn't really need to know that. The server basically just says, okay, I'm getting a message that has 3 packs in it, and packs are just opaque collections of bytes. Strip out that metadata and just store the packs in the database and put the metadata as columns. So the server needs to do very little processing, which is,
Yeah.
by the way, that was one of the motivations for trying to get zero copy reads, because it'd be nice if you could just, you have these big byte buffers in there. That's most of the data. It'd be nice if you could just read those out with having to do a full copy, but it's basically fine.
Yeah. Yeah. Well, and then your server schema is very very basic, and so you don't have to deal with like server schema.
It's basically one table.
issues.
It's like just like updates, and it's huge, and it tells you what the binary data was, what the device was. That's basically it. There's some other accounting stuff, like accounting for the different read heads, and there's if it's stored in S3 where and things like that. But that's basically it. Super simple.
Yeah. Huh. Cool.
So there's 3 of you working in this company, you said.
So there were 3 co-founders. We've since hired 2 other partners, and we're working on hiring potentially 1 or 2 more in the near term here.
Okay, and so how much of your time are you able to spend, like, doing this technology stuff, which you clearly are?
How much time do you spend in the Muse app architecting the system
versus I don't know what else you're doing? I don't know. We'll just call it managing.
Growing up.
Yeah, well, this kind of gets to how we have a very unique setup at Muse. So to directly answer your question, I spent basically all my time on creative work. Now, for me, I'm like a half engineer. I also do product stuff and some other stuff at the company, like I do, or taxes or whatever. But there's no time managing, basically no time managing other people. And this gets to this idea of a partner. So Adam and I, for example, we did a lot of management early in our careers, and that's kind of hard and draining. And like after a while, you get tired of trying to encourage other people to do stuff. And we wanted that world that we call it a partnership, where every single person at the company is entrusted to be a independent high performer, and that's why they're called partners. It's a very high level of responsibility and corresponding high ownership in the company, and so on. And so,
if they need to be managed, maybe they're not a good fit.
Right. Yeah, we don't have time to do that, and we want to work with people who have incredible independent, creative energy, agency, and judgment. I'm so impressed with. It's probably the thing I'm most impressed with the Muse team is the level of judgment that they show. You can just say, like, I'm asking you to decide what to do here. Just please figure it out and make a decision, and it almost always comes back great. It's such a contrast to my old, management world, where everything would need to be like, cross-checked and stakeholders and reviews and reverts and vetoes. And I don't know. So I like the setup that we have of a small number of highly empowered individuals.
So it sounds like you're trying to create a flat organization.
Well, we all know that's a challenge, especially as you get bigger. It's more like the type of business that you're going to have in terms of size and growth is going to dictate the personnel. So if you have a traditional venture-backed startup, like the classic model, the startup needs to become very large, $1 billion plus. The only way to do that is to have a very large team. And the only way to scale in that amount of talent is to have a traditional management structure and so on and so forth. There's also the world, like you can't have a flat organization of 1,000 people. That's not going to work.
There are flat organizations that are a lot bigger than 1,000 people.
They would claim that. Now maybe we can talk more about that. But on the other side, there's the classic indie model of you have 1 or 2 people, they're just doing their own thing independently, and that's great. But there's a pretty limited scope of product and market complexity that you can go after. With Muse, we knew that we were 2 to 3 to 4 years away from realizing the full vision. It would take at least several engineers, take some marketing work, some product work, and design work. It's too big of a problem to do on a fully indie basis. But we didn't want to go and do like the full blown venture capital startup, raise tens or hundreds of millions of dollars and get 1,000-person team. So we've tried to chart this middle path that tries to draw from the best of both worlds. There's like the idea of quick iteration and getting to product market fit and lean that you have from the startup world. There's also the idea of high ownership and responsibility that you have from the indie world and just independence in general, and trying to combine them in this middle path. We'll see. It's honestly quite challenging because of how unusual it is, but that was the idea with creating this partnership.
Yeah, it sounds like something that might scale further than the indie startup model. I mean, it seems like with the indie startup model, you always get to a point where you go, okay, now we have to stick the normal,
Bring in the
yeah,
bring in the managers.
yeah, stick the normal hierarchy in place, and then it's just kind of a giving up process. But here, it seems like you'll probably get further before you decide you have to do that.
Yeah, and certainly 5, 6, 7 people that can operate as a single self-organizing
Mm-hmm.
team. As you get beyond about 7, it becomes harder. You need a little bit more structure. But it's really a continuum where how big are you? How fast are you growing? How sharply divided are the responsibilities and hierarchies? And we're just trying to find a good middle path there.
Well, and it also sounds like the kind of people you're hiring for this may produce perhaps a better corporate culture as the company expands.
Yeah, that's the hope. I feel very lucky to work with the team that we have in Muse.
Mm-hmm.
Awesome. Well, that was great to kind of see how CRDTs can solve real world problems. So thanks for sharing all that information with us, Mark. And yeah, really
and we'll look forward to playing with the app at some point.
We do.
Yeah, because that sounds intriguing.
Yeah, maybe we could use it for organizing open spaces. Something we've talked about for a long time.
Yes,
having the right
electronic organization of open spaces, but we have to have the networked one for that to work.
Yeah, that'd be fun. All right, thank you so much, Mark. Really appreciate your time.
Thanks so much for having me. It was fun.